Is anyone watching the live stream by any chance? Like here? Is someone on their laptop, can they like check to see if it's up or not? That'd be appreciated. It's up? All right, thanks, Ryan. All right, let's get started. So, thanks everyone for coming. This is a pretty good turnout, I'd say. And so today was just going to be the lecture section. So last time I held a review section, we did first half lecture, second half columns. But I felt like with what I wanted to cover, we're gonna run over a lot of time again. So I just decided to split it up into two. So I'm going to be here again tomorrow from 7 to 9 p.m. In the same room, and we're going to be talking about just problems then, and nothing new content for the midterm. So in terms of the midterm, what's on the midterm? I think Davi sent an email yesterday, right? He said something along the lines of, he gave you like all the chapters, he gave you all of the problems, like problem by problem, what's going to be on the exam. So I've seen the exam, that's pretty much what it is. And yeah, I think it should be a fairly doable exam in 60 minutes. That's just my opinion. I would have put harder problems on there, but I think y'all be fine. And let's see, what else? There's going to be a homework due Thursday as well. I would recommend knowing how to do the homework. I would say that if you're, so you should probably just like get the homework out of the way. That would be my recommendation, is just like know how to do the problems on the homework, but just like get those things out of the way, because the homework's more just mechanics. And then I would say for the exam, then go through the review sessions, go through the practice problems, go through the what should we call it, recitations, and see and look at the problems from there. Because I would say across the recitations, these 2 review sessions, and the practice problems, 6 out of the 7 problems on your exam are going to look very familiar, and there's going to be 1 that does not look familiar, but it's not very difficult. So that would be my advice.
They'll look familiar from everything we've seen, or
yeah, from like I said, from the recitations, from the review session problems, and from recitation, review session, and the practice problems cover, I would say, 6 out of 7 problems on the exam. All right. So I know that'll end up being like out of 30, there's going to be 6 of them, but you probably should do all of them anyways. So I think that's pretty fair. So any logistical things about the exam before we start? Yeah.
Is there true false like the last one?
Yeah. There's always going to be true false. It's 240. Yeah, I'm lacking like true false problems on the practice. I might put some more on if I can think of some. Yeah. Homework 6? Is that what you're asking for? Yeah. Yeah. So Zhao hasn't graded. I did not have him graded, but I should have him graded by tomorrow, for my sections at least, by the review session. And then I have been posting the solutions, although I didn't for homework 5, but I'll get to that. So I do have the solutions for like the graded problems on my website as well, so you guys can check those out if you're interested. Because we're not going to grade every single problem on your homework. That just takes way too long. So we only grade like 3 or 4 of them. And the ones that we do grade, I usually just post on the website on how to do them, or like one way to do them. Any other questions? All right, let's get started with material then. So I think the way we're going to do this is that we're going to start with eigenvalues, eigenvectors, and then we're going to jump back to the linear transformations thing. So yeah, why don't we do that? So eigenvalues, eigenvectors. Where we left off, I left off in recitation at least with not enough time to do problems, but all right. So this is chapters 7.1 through 7.3, and I won't go through the definitions of eigenvalues, eigenvectors again, so I'll let you guys do that for yourselves. But let's then talk about the following problems, or the following examples then. So example 1 here, I want to find the eigenvalues and eigenvectors of this matrix A, which is 1, 1, 0, 0, 2, 0, 0, negative 1, 1. Okay, and the problem would just be more or less find eigenvalues and eigenvectors, or diagonalize this matrix, or what's the other one? They might talk about, I think, find a basis for the eigenspace, but that just means find eigenvectors. So, okay. So how do we do these types of problems? They should be fairly routine. So we want to find the determinant of A minus lambda I. So what is that? Well, that's the determinant. So these square brackets, and then A minus lambda I is just on the diagonal, you subtract off lambdas. And then, okay, so everywhere else stays the same. 1, negative 1, 0, 0. Okay. And then what you want to do is, okay, so you want to find what this determinant actually is, which is the following. So, okay, so how do we find this determinant? Well, you probably don't want to cofactor expand. Well, you probably do want to cofactor expand along either the top or the bottom. So it's probably easiest to cofactor expand along there. So we'll take this value. This becomes 1 minus lambda. All right, and then we have this negative 1 to the 1 plus 1 term, right? So that's like the cofactor, the sign, because this is the first column, first entry, and then so that's where you get the 1 plus 1. Okay, and then determinant of the remaining lower matrix. So this is 2 minus lambda minus 1, 0, 1 minus lambda. And then this is equal to 1 minus lambda times 2 minus lambda, 1 minus lambda. Right? And this is a really easy problem to find the lambdas because you just got them right here. So there's no cubics to factor. One thing that you will, or that might happen, is that you might have to factor a cubic polynomial on the exam. So learn how to do those. I told my recitations to do that. But here, what we do then is, okay, so we have to set this equal to 0, right? So it's determinant of a minus lambda I, is equal to 0. So we set that equal to 0, and we solve for lambdas, and so we get lambda is equal to 1, 1, and 2. Okay, so this should be very familiar. And this thing right here, we'll call this the characteristic polynomial. All right, and so now we have lambdas, which are 1, 1, and 2, and we have this repeated eigenvalue with 1. For this exam, I don't think it's very important to worry about repeated eigenvalues, but what we want to see is that, so this is how we write it. We say that lambda is equal to 1 with multiplicity 2, and then lambda is also equal to 2. So what does multiplicity means? Multiplicity just means how many times this eigenvalue appears in our characteristic polynomial. And so multiplicity 2 just means, hey, it appears twice. And this, in the future, will be a really big thing to pay attention to. For this exam, it's probably okay if you don't understand what this means. All right, and why does this multiplicity matter? So why does multiplicity matter? We'll see real quickly. So this step right here, right? This step was finding the eigenvalue. So the next step is finding the eigenvectors. And what I usually do then is we usually case, right, by each eigenvalue or by each unique eigenvalue. So here, right, we have a 3 by 3 matrix, but we only have 2 unique eigenvalues. So let's just so when this happens, when you have a repeated eigenvalue, I never like to case it first, because there's always something up with it. So we're going to case the lambda equals 2 first, since it's not repeated. And what happens when you plug in lambda equals 2? All right, you get negative 1, 0, 0. And then what else? 1, 0, negative 1. And then 0, 0, negative 1. Okay, and so this matrix right here, this matrix is A minus 2I is this matrix. Don't need parentheses around it. So A minus 2I is that matrix right there, right? And to find the eigenvectors, remember, the eigenvectors satisfy A minus 2I times V is equal to 0. And so then this would be the eigenvector. All right, and this would be the 0 matrix. So essentially what we want to do is we want to find a vector v that's in the null space of A minus 2I. Okay? So how do we do that? Well, you can think of it as this matrix, right? We're trying to solve the homogeneous system with this matrix. So you can think on the right-hand side, we have zeros. Right? So you can think that we have some augmented matrix with the zeros on the right-hand side, and then now all we have to do is solve this homogeneous system. And this is where homework will help. This is where doing problems will help. But what you want to do is you want to get comfortable with just being able to eyeball a solution for this matrix. Okay? And we can see that then if I let v, and let's call it v1, be 0, 1, 0, that's going to be a solution to the system. Right? Because what happens is you're taking each row and you're multiplying it by this eigenvector, right? So you'll have -1 times 1, 0 times 1, or -1 times 0, 0 times 1, and then here you'll have, what color should I use? Let's use blue. 0 times 0, right? So that will get you this 0, right, if you sum them up. And then likewise, if you just go down for each row, right, -1, you got 1 times 0, 0 times 1, -1 times 0, so that's 0 plus 0 plus 0 again. And then likewise for the last row, you'll just end up with 0 plus 0 plus 0. So what you want to see then is, okay, so my middle column is 0. That means for my second entry, I can just put a 1 here, and then I'll be done with it. Yeah.
Can you put whatever number you want?
Yeah, you can put whatever. Yeah. So you can put like 7. You can put -14. It doesn't matter. The reason why we put 1 is the whole idea of diagonalization, which we'll get to in a little bit. Yeah, David?
Could you do free variables to solve that?
Yeah, you can do free variables to solve that. There's nothing wrong with that. Yeah. Any other questions? Okay, so what? Okay, so that's lambda equals 2. You got your eigenvector. It's this mess right here. Let's clean it up a little bit. So that's my first eigenvector. Now we have to deal with the lambda equals 1 case, which I put off. All right, so now what is lambda equals 1? Well, you get this matrix. You get 0, 0, 0, 1, 1, -1, 0, 0, 0. Right, from a minus lambda I, so if you go up here, right, you subtract 1 off the diagonal, that's what you get. So you get this guy. So this is a minus 1i. Okay, so let's make an observation then. What is the rank of this matrix? 1, right? Okay, so by rank nullity theorem, what does the nullity have to be? 2, right? Okay, so yeah, so let's write that down. So we have nullity equals 2. But what was this brand new word that I just introduced earlier? And what value was that? Yeah, multiplicity, and what was its value? It was equal to 2, right? Okay. So yeah, so nullity is equal to 2, and we also know that multiplicity was equal to 2, and I always abbreviate multiplicity as mult. Right, so we know nullity equals 2 and multiplicity equals 2. What does this tell me? This tells me that since these two are equal, this tells me that I have 2 linearly independent eigenvectors in the eigenspace for lambda equals 1. Okay, and it's not really that these two. It's not really that these two have to be. So this value really tells me that I have 2 linearly independent eigenvectors in the eigenspace. Yeah.
Does the nullity include the 0 vector?
What the nullity?
Or does the 0 vector in the null space contribute?
No, it doesn't. It doesn't. Yeah, the 0 vector. So if you ever have a null space with just the 0 vector, the dimension of the null space is 0. Okay, because if you think of it, the 0 vector being the only solution means that it's just a point at the origin, right? So a point has no dimension. Okay, so why does this matter? So okay, so nullity equals 2 tells me how many linearly independent eigenvectors are in my eigenspace for this particular lambda. These two being equal means okay, so these two being unequal means not diagonalizable. Okay, something's going on. Not able to erase. All right, so if if you ever run into a situation where your lambda, right, the multiplicity on your lambda is not equal to the nullity of the corresponding A minus lambda I matrix, then that matrix is not going to be diagonalizable. And for the purposes of this exam, you don't have to know what to do after that. You only need to be able to recognize that this could happen, but you don't have to know, like, oh, how do we get around the fact that it's not diagonalizable? Okay? But for now, just know that, hey, if I have a repeated eigenvalue, right, how many times is it repeated? That's the multiplicity. And then that has to be equal to the nullity of A minus lambda I for that eigenvalue. And if it's not, then it's not diagonalizable. If it is, well, that doesn't tell me anything, because every single eigenvalue has to have this condition satisfied for the matrix to be diagonalizable. We'll see this in a bit. Yeah.
The diagonal as ability, is that related to being defective?
Yeah. So not diagonalizable means defective.
Okay.
Yeah, but again, we don't really have to know that for this exam. For the next one, it's going to be a lot more important, though. Okay, so anyways, I've been harping on this a little bit. It's again, not that important for this exam. Just know that nullity should equal multiplicity here. And okay, so now what do we do? So now we need to find two eigenvectors in the null space of this matrix. Right, so essentially we want to solve this system. All right, and so how can we do it? Well, again, we can just solve it for, just like the free variables in terms of free variables and solve it that way. But let's try practicing eyeballing this. So let's have V2. All right, let that be our second eigenvector. And does anyone see a possible solution for the second eigenvector? Yeah, let's go.
1, 0, 1.
Yeah, so 1, 0, 1, right? And how'd you come up with that one?
If x1 and x3 are both 1, then it zeroes out.
Yeah, exactly. If x1 and x3 are both 1, they zero out, right? Because 1, 0, negative 1, right? And that gives me 0. And this is the only row. The second row is the only row I care about. Because this first row is always going to get me 0. This last row is always going to give me 0. So this eigenvector only needs to satisfy the condition on this on row 2. So essentially what you're doing is you're taking a dot product of this row vector and this column vector, and you're going to get 0. And it doesn't matter how you get there. Okay? So that's one of them. We need another one now. So that's V2, so this one has to be V3. Okay, any other one? Yeah.
1, 1, 2.
Yeah, 1, 1, 2, so that works too. 1, 1, 2, right? And the same idea holds because now you have, what do you have? You have this 1 times 1, 1 times 1, so 1 plus 1 is 2, plus a negative 2, and so that gets you 0 as well. Okay? So when you have, the one thing that you can't do is that you can't choose V3 to be like 404. Okay? Because then they're the same thing, right? Essentially what we're trying to do is you're trying to find a basis for the eigenspace, and if you have two linearly dependent vectors, they can't form a basis, right? Because the first condition for basis is linear independence. So so here, nullity being equal to 2 tells us that I have two linearly independent vectors, and so now I just have to be able to find what the two linearly independent vectors in my eigenspace are. So instead of 1, 1, 2, you could have picked 1, 0, 1, negative 1, 0. Right? So it could have been 1, negative 1, 0. That would have been fine. But then if you have 1, 0, 1, 1, 1, 2, you can't also put 1, negative 1, 0 because these two already span the entire eigenspace, and 1, negative 1, 0 is just a linear combination of these two vectors. So, all right, so we found lambda. Okay, so now we have, so what do we have? We have lambda is equal to 1, 1, 2, and then we have the corresponding eigenvectors, which are, I don't know why the eraser's not working, but anyways. So now we have, okay, so one of the eigenvectors that corresponds to 1 was 1, 0, 1. One of the eigenvectors that corresponds to 1 was 1, 1, 2. And then the eigenvector that corresponded to 2 was 0, 1, 0, right? Okay. All right, so diagonalizing a matrix. Diagonalizing a matrix. We just do the following. We just say, all right, so if we have linearly independent eigenvectors for every eigenvalue, we can diagonalize the matrix A where the eigenvalues and eigenvectors came from. Okay, so if we have, if we have linearly independent eigenvectors for every eigenvalue, which is the case up here, so that's this case right here, right? Every eigenvalue has its own associated linearly independent eigenvector, then we can just diagonalize a matrix. And so what does that mean? That means that A, all right, so A is our original matrix, is equal to S D S inverse. Okay? And what does this mean? This just means that, okay, S is a basis of eigenvectors. D contains the eigenvalues as a diagonal matrix. And then S inverse is just your S guy, just inverted. So how do we actually diagonalize this matrix? So, all right, so here's S, here's D, here's S inverse.
What does it say for D?
D is eigenvalues as a diagonal matrix. Yeah. Okay, so what do I want to do? All right, so let's start. And the easiest thing to do is to put your make your D matrix here. All right. So for the D matrix, again, we just put our eigenvalues on the diagonal, and it doesn't matter what order you put them in. Here. All right. So we can do 2, 1, 1. We can do 1, 1, 2. We can do 1, 2, 1. It doesn't really matter. So let's just change things up. So let's do 1, 2, 1. Like it literally doesn't matter right here where you put them. As long as you put your eigenvalues on the diagonal, you're fine. Yeah.
Just going back to the eigenvectors for 1.
Yeah.
If you did that in a way with S and T, you would get different ones.
Yeah, it doesn't matter, right? Because I said that you could have picked 1, negative 1, 0,
Okay.
right? Instead of 1, 1, 2, right? The thing is, if I have 1, 0, 1 and 1, 1, 2, then 1, negative 1, 0 is a linear combination of those two that I already have.
But if you have like negative 1, 1, 0, and 0, 0, 1.
Negative 1, 1, 0. I mean, yeah, but it's fine. So
Same thing.
yeah, you just need to pick two linearly independent ones, right? So the thing with these types of problems is that you have a lot of leeway in, like, especially when you have a repeated eigenvalue, you have like leeway into which eigenvector which two eigenvectors you pick. Because our eigenspace for lambda equals 1 is 2-dimensional, right? So it's a plane, and there's infinitely many vectors you can choose on the plane. So you just have to choose two of them.
I was just confused because I didn't see like single without this.
Right. Okay. Yeah.
So the second eigenvector for, like, say, lambda equals
It has to be. It has to be. Yeah. If you can make, like, if lambda equals 1 and 0, 3, 0 is an eigenvector for lambda equals 1, you get it wrong. All right? So across all of the eigenvalues, they all have to be linearly independent. Because why? We're putting those eigenvectors into this S matrix right here. What do we have to do to this S matrix? Yeah, we have to invert it, right? So if any one of those are linearly dependent among each other, then you can't invert this matrix, right? So they always have to all have to be linearly independent. Okay. So all right, so we did this. We put the eigenvalues in the D matrix. Literally just threw them in whatever way I wanted to. So now what happens? Well, this being a 1 here indicates that this first column has to be an eigenvector corresponding to lambda equals 1. Okay? Again, but it doesn't matter which one of the two I pick for now. Okay? So does anyone have any eigenvector they want to throw in that first column for S? So I heard someone mumble 101, why not? So we'll put 101 right there. Okay? Then here, for 2, right? So 2 is in the second column of D, which means that the eigenvector corresponding to lambda equals 2 has to go in that middle column. So this one has to be 0, 1, 0. And then lastly, got lambda equals 1, but I already used this guy, right? So I can't put 1, 0, 1 in again. So I have to use 1, 1, 2. Which then is the last eigenvector that corresponds to lambda equals 1. Okay, and then that. And on most problems, what they're going to ask is that they're going to ask you to find an S and a D. All right? They're not going to ask, so you don't really have to find S inverse. That's not like the point of the problem. All right? So the problem will just be find an S, find a matrix S, find a diagonal matrix D such that SDS inverse is equal to A. Okay? There's other ways they could write it, so don't be fooled. You could see like AS is equal to SD, SD is equal to AS, right? That's just moving the S around, moving that S inverse around. Okay, and then also equivalent, you could be asked, what is S in? You want to find something such that S inverse AS is equal to D. So these are just all permutations of like multiplying S's around. These three are all equivalent. These four are all equivalent to each other. You just do this. Yeah.
Because your D had been 1, 1, 2.
Yeah, it literally doesn't matter what our D would have been, but if it were 1, 1, 2, then this column had to be, yeah, it has to go somewhere else. It has to go where the 2 is. All right, and then for the sake of time, let's just not worry about that S inverse matrix. All right, is everyone cool with diagonalizing? Any other questions?
Just all the diagonal matrix is. It's just the eigenvalues.
Yeah, it's just eigenvalues.
Okay.
Yeah. And those determine where your eigenvectors go in S. All right, so that's diagonalization. If there are no questions, we'll move on. So we'll move on to another matrix here. We'll let A is equal to 1, 2, negative 2, 1. All right, and so now you want to find eigenvalues and eigenvectors. All right, so what is the determinant of A minus lambda I? You get 1 minus lambda, 2, negative 2, 1 minus lambda here, and then you can just multiply this out. So this is 1 minus lambda squared plus 4, which is equal to lambda squared minus 2 lambda plus 5. Okay, so this is our characteristic polynomial. It needs to equal 0. What are the roots of lambda? So yeah, so sometimes this doesn't it doesn't work out nice. So what we're going to have to do is that we're going to have to go to our, I think, Algebra 2 toolbox from high school. I'm going to have to bring out the quadratic formula, right? So lambda is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. And insert your favorite tune that you learned how to memorize this. So what is this? This is 2 plus or minus root 4 minus 20 all over 2. And so this becomes 2 plus or minus root negative 16 over 2. And that's 1. So before we get that far, 2 plus or minus 4i over 2. So you get 1 plus or minus 2i. Okay, so you run to this case where you have complex eigenvalues. And these are absolutely a pain in the rear to deal with. But in terms of finding eigenvalues, eigenvectors, they're like kind of fine. Where it gets really annoying is when you have to find exponentials, whatever. Don't worry about those. So, okay, so now here's my lambdas. And so now I need to consider one of the cases. And let's consider then 1 minus 2i as my eigenvalue. Okay, so if you remember, here's the a minus lambda I, right? So this is really a minus 1 minus 2i big I. So on the diagonal, we're subtracting 1 minus 2i. So this is like 1 minus 2i, 2, negative 2, and this is 1 minus 2i. Okay, and then that's equal to 2i, 2, negative 2, 2i. Okay, so now what? Okay, so now we need to find eigenvectors, right? And so we essentially have an augmented matrix with the zeros at the end. And this is a case where you can actually just eyeball what's going on. So I don't think there's going to be, if you guys do get a complex valued eigenvalue type of problem, this matrix shouldn't be too bad to calculate. But essentially, we can try to row reduce this to see what's going on. So 2i2, and on this bottom, how do we zero out this entry? Yeah. Yeah, okay, yeah, so you can do minus I times first row, and let's do that. So you take row 1 times row 1 times I. So we replace this second row with row 2 minus I times row 1. All right, so this becomes 0. And how does that become 0? This is really negative 2 minus 2i squared, right? Which is negative 2 minus a negative 2. So that's negative 2 plus 2. And so that's how we end up with 0 there. that means over here I got 2i minus 2i. All right, so we end up with 0, 0 on the bottom. So now we have this case where we have 2i, 2, 0, 0. All right, here's a pivot, here's a free, and we need this to end up equaling 0, 0. So then from row 1, we see that, okay, so if we let x2 equal t, then x1, so 2i x1 plus x2 is equal to 0. 2i x1 is equal to t, or negative t. And so x1 is equal to negative t over 2i. Oh, wait, this should have been 2x2. This is 2t. This is negative 2t. So that's really negative t over I. Okay. And then, so now what? So now we got x, or our eigenvector v is equal to x1, x2. That's a very poor choice of indices or letters, but that's fine. And then so you got t, and you got negative t over I up here. So you want to rationalize that denominator. So you want to multiply the top and bottom by I. And so what you get then is you get negative ti over I squared. T, and I squared is negative 1. So this is actually ti t. Okay. And then, so now what? So now we just have to let t be something. So if we let t equals 1, then v is equal to I comma 1. And so that's v1. Okay, so now we have to find v2, right? And to find v2, right? So one would think to find v2, we would go all the way back, right? We would go all the way back here. We would plug in lambda equals 1 plus 2i and go through all the motions again, right? But we can exploit a useful characteristic of how these eigenvalues are coming up. Does anyone notice how the eigenvalues are showing up when you have complex eigenvalues? Yeah. Yeah, they're complex conjugate pairs, right? So when you have 1 plus 2i, you have to have 1 minus 2i. And that's because all the entries in A are real. Okay, so if all of these guys are real, then you'll have a conjugate pair show up. So that just means that, hey, I have 1 plus 2i, so then my other eigenvalue is 1 minus 2i. But essentially what's going on is that all your i's are getting flipped by a sign, right? You guys see that? How the eigenvalues, when they show up, the i's are just flipped by a sign. Well, it turns out if you work through everything, all that's going to happen is that all your i's are just going to flip signs. So that means this eigenvector at the end is just going to have a flipped I. So v2 is just automatically negative I comma 1. And you can always use this when you have complex valued eigenvalues. That come in conjugate pairs, which is the only way they'll show up in this class. Okay, so this is v2. And this was lambda equals 2 minus 2i, right? And 1 minus 2i. And so this one corresponds to lambda equals 1 plus 2i. And then the same idea holds if you want to diagonalize your matrix. All right, we can put our eigenvalues in. So let's just do, for sake of things, 1 minus 2i, 1 plus 2i, 0, 0, right? And then this has to correspond to 1 minus 2i, so this is I1. And then the second column has to correspond to 1 plus 2i, so that will be the second eigenvector, I1 negative I1. So this is an example with complex values as your eigenvalues. All right, and one really annoying thing is that you see that S matrix. It's really hard to invert when you have complex valued eigenvalues, right? Like you have i's everywhere. So when we actually use matrices with complex valued eigenvalues, we usually do not actually diagonalize them because that S inverse doesn't really help us. But for the sake of this exam, if this shows up, this is what you have to do. Okay, any questions here? Yeah, right.
When you did the 1 plus 2i,
Yeah.
How did you automatically know that it was just going to be the negative version of it?
Because my eigenvalues are coming up in conjugate pairs, right? Complex conjugate pairs. So I calculated the one for 1 minus 2i, right? But what's different about the other eigenvalues? It's just the positive version of it, right? And so all your i's just get flipped. So if you work through all of this crap with 1 plus 2i instead of 1 minus 2i, you'll notice that all your i's are just going to get flipped. So like this.
That's always going to be the case.
That's always going to be the case, yeah. So this is going to be negative 2i, that's going to be negative 2i up there. And there's no reason in doing that, right?
Okay.
Because you can just then go to your eigenvector, and then you can just flip that I around. And so if this were something like 7 plus I, then this entry would just be 7 minus I. You just literally just flip that sign on the I. Yeah, I saw a hand go up down here.
Oh, I have the same question. It's always the case.
Yeah, it's going to be the case because as long as these guys come in a pair, which to my knowledge that always happens in this class, so you wouldn't have to worry about anything weird coming. Yeah. 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 Yeah.
Is it wrong if you just remove t at that point and then you would end up with like -1i as your eigenvector?
I think -1i works. It does work. Yeah, yeah. So when you have I, it's kind of weird because the one I have on my sheet is actually 1 negative I, but you give me -1i, which is just -1 times what I have. So I know that would work for sure. Yeah. So it doesn't matter. Honestly, the best way is just to try to eyeball it, because then you would have come up with I1 almost immediately, because I squared is -1. So then you had -2 plus 2, right?
There's multiple answers.
Yeah, there's multiple answers. Exactly.
So is this all of chapter 7 that we need to know for this test?
Yeah, more or less.
And then, so a question would just be to find like the A equals S ds inverse.
Yeah, find S and D such that A equals S and S.
Okay, so that's what this is.
Yeah, I was just wondering, of those two green lids that you have,
Yeah, so
what are they?
I'm just saying that this is a pivot column and that's a free column. So P and F. That's how you use it to know. Yeah.
Can you explain again why unity and multiplicity are not equal, then they're not diagonal?
Yeah, sure. So the question is, if nullity and multiplicity aren't equal to each other, right, then why does it mean not diagonalizable, right? So let's go to this example again. When I put, okay, so nullity, right, tells me how many linearly independent eigenvectors are in the eigenspace, right? Or in the null space for a minus 1I, right? Okay. So multiplicity tells me how many times that eigenvalue is going to show up, right? So multiplicity 2 just means 1 showed up twice, okay? And then when you notice, when you're diagonalizing this matrix, right, 1 has to be associated with 2 linearly independent eigenvectors, right? But the nullity tells me how many linearly independent eigenvectors there are, right? So if the nullity was 1 and the multiplicity was 2, I wouldn't have this thing, right? And then you have this problem because you can't throw this into STS inverse because this vector just doesn't exist. You can't. It's not possible to find this vector. Is that good? All right. Any other questions? Okay. So why do we care? So why do we care about diagonalization? Really, so for the purpose of this exam, there's only one reason why we care about diagonalization, and it's the following. If you want to do like a to like the 70th power, all right? So if some problem just asks you, oh, what's a to the 70th, right? You can sit there and multiply a by itself 70 times, and you won't get any other problem on the exam correct, right? Because you're just going to run out of time. But we can leverage the fact that a is equal to SDS inverse, right? So then what is a squared? Well, a squared is just going to be SDS inverse times SDS inverse, right? Since we said a was SDS inverse, right? So now a squared is SDS inverse times SDS inverse. What happens is that S inverse and S cancel. They're the identity matrix. So now you have SDDS inverse. But d times d is just d squared, so this is equal to SD squared S inverse. And now you see, if we keep on going on, if we do a cubed, then that's SDS inverse, SDS inverse, SDS inverse, right? That cancels, that cancels. You got SDDS inverse. That's equal to SD cubed S inverse. Right? So what can you do then? Well, then what if I have a to the k, what do you guys think that's going to be? Or actually, let's go back up. A to the 70th. What do you guys think a to the 70th is going to be? Yeah, this is SD to the 70th S inverse. All right. And why do we care about, why do we want to do it this way? Okay, this pen's. All right, so why do you want to do it that way? Why do we want to do it SD to 70th S inverse? It's because if you take a diagonal matrix and you multiply it by itself, right, it's just equal to the entries, like, to the whatever power. So if I took 1, 2, and raised it to the 70th, that's just equal to 1 to the 70th and then 2 to the 70th on the diagonal. So it's a lot easier to compute these kinds of matrix powers, and this is how like your computer kind of does it when you have to ask it to compute a matrix power. So this is what you want to do, and this is like, so for this exam, this is probably like the only type of like diagonalization, like application that you have to know. There are others, and there's one that will take over the rest of the course in a little bit. Any questions about this? Okay, that's all I want to talk about diagonalization, eigenvalues, eigenvectors. There are other videos online. There are more examples there. There are definitely examples on the practice problems, and so we're going to move on from this. So what I'm going to do is I'm going to take a 5-minute break real quick, and then we'll continue. We're going to talk about linear transformations, and we're going to talk about change of basis. So yeah, so let's take a break. Let's say 5:10. Well, when I'll resume.
Okay, so change your basis, John, right? Did you do that yet?
No, not yet. No, I'm good.
Okay. No, not here. Just did you do it in class? Stuff is about 6 is about complex basis.
Linear transformation. Yeah.
Okay. And 4 is about more, right? Or 7 is
No, 4/7 is change of basis.
Alright, whatever. I was doing a question. I was just like, but that's it for chapter 7. And could there be exponential relations on?
Yeah, exactly. That was like the only application. Yeah.
So like if there's like a question like were to say like find an A or find an S and D such like this and then find A to this,
Yeah.
like or would it just say find A to this?
Well, if it says just find e to the blank, you know, you can do this. Yeah.
But you have to find the S inverse to all of them.
Yeah, you would need to find S inverse, but like at the end of the day, that's a lot better than multiplying A by itself.
And like so on like my homework I was just looking at physical problems and there's stuff about like the inverse transformation.
Yeah.
Like we already talked about that in class. So is that stuff we would need to know for the test?
I mean, it's just think of it as another map. Just maybe don't think of it as T inverse, right? You have T and T inverse. Think of it as like V that sends V to W to V instead of V to W.
Oh, okay.
Yeah, it's just a different name. T inverse is just the name.
Oh, okay.
Yeah, don't get too caught up in like.
And if I can
Well, you need to use that fact later on, like in the problem to help you, like show that it's a linear transformation, but like it's not. It's just there, like it's not like an explicitly like explicit concept you need to know. You just do like it's just you just do show linear transformation.
I was just wondering, so if you get complex values for your eigenvectors, I think I saw this, or like in my head I had like you had to have real distinct eigenvalues to have a matrix be diagonalizable, but that's not true.
For every eigenvalue, you just need an associated eigenvalue.
Okay, so it can be complex, and it's fine. Okay.
Yeah, but it's just that we never actually diagonalized complex eigenvalues because I said you had to take S inverse of this matrix that has complex values.
Then you just end up it's -5 to 50. Also on the previous question on the final, so even my friend found this by just doing a guessing check forever, but is there when you get out of that part? So I'll say
by A, like it always says you have A, and then it ends up in B. Like the vector on the times that vector is the new vector. Why is it every time two vectors is the whole vector? Doesn't make any sense.
Linear transformation is A times But then you can just leave it as like 2 to the 17th. Right? You don't actually have to tell me what 2 to the 17th is.
Right. So like, I still wouldn't be able to believe what 8 is.
The math part of it is fun,
Yeah. But I mean, S inverse is a lot easier to find.
And like you have to drag it, you have to do that.
Yeah, exactly.
Then that
Okay, let's continue. So, I'm going to continue. I'm going to talk about change of basis first. It's a special type of linear transformation, but I don't So a lot of people are like always very concerned when there is a change of basis problem, but I think just calculating it isn't that big of a problem. So we'll see here really how we calculate change of basis. So what is change of basis? What's going on is, imagine you have the xy plane. Actually, you know what? Let me calibrate my thing first, because we're getting a lot of lag. Okay, so imagine you had, actually, we can make this better. Rule lines. Nice. Okay, so we have this xy plane, right? And it usually, what we do is that we have our standard basis for the xy plane, which is the following, right? We have our basis be 1, 0, and 0, 1, right? So this vector is really 1, 0, and this vector going up is 0, 1, right? And we're comfortable with this because I can pick a point out in space. Let's call it, let's pick a point right there, right? This point, in terms of this basis, is 3, 3, right? But really, what does 3, 3 mean? It's really 3 times 1, 0, comma 3 times 0, 1. Right? Or we're really adding, actually, I did that wrong. It's really, we're really adding 3 times 1, 0 plus 3 times 0, 1 to get 3, 3. Okay? But now what happens if, let's say, I define my bases differently? Now, if I define my basis like this, all right? So now this is, let's call this x bar and this y bar. Okay, so I've changed my basis, how I'm defining this. This basis, let's say this basis here, this is 1, 1. And this basis going this way, this can be negative 1, 1. All of a sudden, this point here, 3, 3, is not 3, 3 anymore, right? But instead, it's something, it's x times 1, 1 plus y times negative 1, 1. Right? Since x is going to multiply by whatever the basis for the x-axis is, so that's 1, 1. Right? And then y will multiply that by whatever the y basis is, which is negative 1, 1. Okay? So can we just eyeball what x should be and what y should be? In this case? What should it be? 3, 0, right? So x should be 3 and y should be 0, right? Because if you add this up, this is equal to 3, 3, and if you add this up, this is also equal to 3, 3. We're just expressing, instead of expressing it in terms of the old basis, right? So up here, we took this and put it here. We took this and put it here. In terms of the new basis, we have to take the 3 and put it there, and we take the 0 and we put it in the y entry. So under the new basis, this point is actually 3, 0. Yeah.
Are the x and y that you multiply by x bar and y bar?
No, I should have called it something else, right? We should call it like C1 and C2. They're just random constants. We just have to find. We just have to find what C1 and C2 are. So it ends up being C1 ends up being 3 and C2 ends up being 0, right? And then this new point is 3, 0. So how do we express this? Well, essentially the textbook will do this. The textbook would say, all right, if you let basis be, and this is how it'll be like on the exam, be 1, 0 and 0, 1, right? And basis C be 1, 1, negative 1, 1. All right? Then if you know that VB is equal to 3, 3, they'll ask you to find what VC is equal to. All right? And VB, this just means this right here, expressing 3, 3 in terms of the original basis, in terms of the B basis, and then VC is just expressing 3, 3 in terms of this new basis here. So VC would be 3, 0, right? Because we're expressing VC in terms of the new basis, yeah.
So would we ever get questions like asking us to like take one point and find it elsewhere?
Yeah.
The question was like VB equals XY, find like what VC would.
No, they'll give you like they'll give you
like,
BC and they'll give you like VB and then you have to find VC.
Okay.
Essentially, that's what they'll do.
So the basis for C, did you just, like, was that still based on, like, the normal XY coordinate to get
Yeah, it was, right?
That's, like, something that you...
That's they'll so
You didn't
at some point, like, we have to go down to the question of what does 1 mean, right? And so, yeah, everything is, like, C being 1, 1 is actually, like, expressed in terms of the basis in D. Does that make sense? Like, these vectors are actually being expressed as, like, a combination of these guys, but then C, VC is expressed as a combination of.
So C doesn't always have to be based on B. It's just because we chose B to be the natural
Basis, yeah, exactly.
So B could be, B and C could be like fully.
Yeah, B could be literally anything. Okay, because now I can just like it's easier to. This is just a visual example, right? So the question then is, okay, so we were able to do this visually, but how would we do it not visually, right? How do we do it in terms of matrix multiplication? So that's the following. So let's get rid of the grid lines. So change of basis is the following. We say that VC is equal to PBC times VB, where PBC is a change of basis matrix. Okay? So, and the way you should think of it is like you should draw an arrow like that. So we go from B to C. The other way that the textbook doesn't use that I actually prefer a lot more is if you use P, B arrow C, because this is literally telling you you go from B to C, right, with the arrow. I think that's a lot more clear.
So the horizontal arrow encompasses all of the second part, or you still have to do the...
No. I'm just saying that these two are equal to each other.
Okay.
Yeah, I'm just saying those two, like, expressions are equal. The PBC and the PBCs are equal to each other. Okay, so how do we find PBC? We do it the following way. So finding PBC or P B arrow C. So again, so what's my basis up here? Let's just rewrite it so we have it. So we have B is equal to 1, 0, 0, 1. And then C is equal to 1, 1, negative 1, 1. Okay, and like the reason why, so I was going to teach this in terms of a linear transformation, but the reason why I didn't is because if I taught in terms of linear transformation, it's like backwards. So I didn't want to deal with that. So just blindly follow this way. PBC is a linear transformation, but if you just blindly follow this method of finding PBC, like you'll be fine. Otherwise, you're just going to be wondering like which vector goes where am I supposed to multiply this matrix? It just turns out to be a mess. So if you follow this, you'll be fine. So how do we find it? You take your basis for C and you put them on the left. You take your basis for B and you put them on the right. And that's why this notation is so good. It's because you know where to put B and where to put C. So, but for some reason, the book likes to do it that way. All right, so now what do we want to do? All right, so B is 1, 0, 0, 1. C is 1, 1, negative 1, 1. All right, and now we row reduce. So what do I want? I want the left-hand side to be an identity matrix. So then 0, 2. And then this would be negative 1, 1. And then you get 1, negative 1, 1, 0, 0, 1, negative 1 half, 1 half. All right, we'll keep on going. So now this becomes 1, 0, 1 half, 1 half, 0, 1, negative 1 half, 1 half. All right. Here is your identity matrix on the left-hand side. And on the right-hand side, you have good old PBC. All right, and did this work? Well, let's find out. So again, I said up here, right, that VC is equal to PBC times VB. So I claim that VC is equal to PBC times VB. Right? Okay. So VB is this guy, right? The 3, 3 vector. So this point out here. And if I multiply my change of basis by this, if I multiply change of basis on the left, this guy on the right, I should get 3, 0. Right? So that's what that's telling me. So now, what do I have? I have 1 half, 1 half, negative 1 half, 1 half. All right, VB was 3, 3. Three halves plus 3 halves. Negative 3 halves plus 3 halves. 3, 0, which is VC. Right? So what did I do? This matrix multiplication essentially took me from the black bases to the orange bases. All right, are we cool with that? Is that fine? Yeah.
Is the black one always going to be the 1, 0? It doesn't even matter. 1, 0, 0, 1?
No, it's not. It's just for this example because we could eyeball it, right? We could eyeball what's that change of basis, what like the answer should have been, right? And this was just, so that picture is just a verification that this works. The process is the exact same. You set up C on the left, you set up B on the right, or whatever the hell. If they make you do like P, Q, R, right? Then you put R on the left and you put Q which is this point in green expressed in our original basis B, right? And now we want to express that point in the basis C, right, which is the orange basis. So then I have to multiply this change of basis matrix by that old vector, which is VB, and now 3, 0 is my new coordinate in terms of the orange basis up here. Is that?
How did you get from the 3 halves matrix?
These are adding. This is just matrix multiplication right here. Yeah, my bad. Yeah. I literally just multiplied these two guys together to get here, right? Because now these are just adding, right? 3 halves plus 3 halves, negative 3 halves plus 3 halves. Yeah. Right. Yeah.
Does the order of the vectors within B and within C matter?
Yes, they do. The order does matter for this. So however they, like in the order they give it to you in the problem, you have to set it up that way. Okay? I think there is a problem on the practice exam, or not the practice problems where like this order thing kind of gets thrown into play. Yeah.
Are you going to do examples where you don't go through like the same like vector space?
No. So change of basis has to be within the same vector space, right? Because you're changing the basis of that vector space, right? But yeah. So I'll do an example where you have a linear transformation between different bases. That's a different thing.
What order matters?
Or like the order that the bases are given to you, right? So I gave you this as 1, 0, 0, 1, and this was 1, 1, 1, negative 1, 1, right? But if I said, if this order of, so this is why order matters, is because if this wasn't 1, 1, but this were negative 1, 1, and then this guy were 1, 1, then all of a sudden, that vector is not 3, 0. What is it? 0, 3, right? Because I switched the order of the bases around. So yeah, you do need to pay attention to like what order the bases are given to you in, and that will change the result of the problem. But in this case, that's 1, 1. This is negative 1, 1, and so everything's okay, I think. Any other problems? We'll do another example. So this was the part of the homework that you guys didn't have to do. But this was spring 2016 final, right? And it was that like whole like subspace of matrices things. So you had B was equal to these matrices. And then C was equal to these matrices. Right, so you had some matrix for a basis that was B. You had some matrices that for a basis that was C. So part A of the problem was like show that C is a basis for the subspace. Right? Do you guys vaguely remember doing that or copying that from whatever I have online? Right, so part A was show that C is a basis for the subspace. Part B, which you guys didn't have to do, is find a change of basis matrix P B C. Is that handed back? All right, so how do we find a change of basis matrix PBC? Well, we're finding a change of basis matrix between matrices, which is always weird, right? It's always awkward. But what do we do when we have like matrices in our basis? Yeah, you unravel them, right? So, all right, so we'll write B is equal to 1, 0, 0, 0. 0, 0, 0, 1, 0, 1, 2, 3, or 0, 1, 2, 0. So you have to unravel everything the same way. Okay, that's just a heads up. So for example, so for C, right, I have to write 1, 1, 2, 1, 1, 0, 0, 1, and 0, 1, 2, 3. Right, so so for both these guys, I did, right, first row went here, second row went here, right, in order from left to right. So you have to do that then for everything. Otherwise, you're not going to get the right answer. Okay, so if you just stick with one way of unraveling the bases, which is like the way I showed you, then this won't ever be a problem. Okay, so we need to find PB to PC. So what we do then is, right, so we throw these into this augmented matrix. 1, 0, so I did backwards, right? Because it's C and then B. Because you go from PB to PC, or you go from basis B to C. Right? And so now here's a case where B isn't the standard basis, right? So we see something different. So what happens? All right. You got 1, 1, 2, 1, 1, 0, 0, 1, 0, 1, 2, 3, 1, 0, 0, 0, 0, 0, 0, 1, 0, 1, 2, 0. Is there a problem here? Yeah.
Don't you need to reduce it to the identity matrix?
Yeah. You can't do that, right? Can't reduce that to the identity matrix because it's a 4x3 and we need a 3x3 or a 4x4. Any ideas on how we proceed here? Yeah. Yeah, so the second and third row are like the same thing, right? The second row is just a multiple of the third row. All right, and here's another way to think about it. So do we like, so I'm saying get rid of a row, right? And then we'll end up with a 3x3 matrix, right? So that, everyone seems okay with that, right? Okay. Why are we not just randomly adding a fourth row and getting a 4x4 matrix? Or a fourth column. Why are we adding a fourth column to get 4x4? Why are we reducing a row to get 3x3? Yeah.
Wouldn't that change your vector space?
I mean, if I made it like, well, yeah. So that's one way to think about it, right? But the other way that I want to point out is, what's the dimension of B? 3, right? B has 3 elements in it. What's the dimension of C? It's also 3. All right? The change of basis matrix has to reflect the dimension of your vector space. So that means PBC has to be 3x3 because B, right, is dimension 3 and C is dimension 3. All right? Remember with the whole linear transformation thing, I was like, okay, you got to think about like dimension of your input, dimension of your output. That tells you what the dimension of the matrix of transformation is, right? Well, here, because we're within the same vector space, it has to be a square matrix. The change of basis matrix has to be square. All right? So it must be square. Okay, so how do we make a square? Well, since it has to be dimension 3, it must be a 3x3 matrix, so we can just get rid of one of these rows. Let's get rid of that row. Okay? So now we need to make a note to ourselves. Note, there exists a fourth row, or a third row, but it's 2 times row 2, right? That third row is just row 2 doubled. Okay? So now what? So now we end up with 1, 1, 0, 1, 0, 1, 1, 1, 3, 1, 0, 0, 0, 0, 1, 0, 1, 0. Okay? So now we reduce 1, 1, 0. So this becomes 0, 0, 3, right, on the bottom. And negative 1, 1, 0. And then up here it is 1, 0, 0. And the second row, this becomes 0, negative 1, 1, negative 1, 0, 1. Yeah.
Is there ever a situation where we have something similar to this, except we have the limit of the row?
No, because then there wouldn't be a basis for the same vector space. It won't ever happen. Yeah, that's what I'm trying to say.
Sorry, what's the question?
The question was, like, is there a case where, like, this, like, you know how I just drew a line through row 3? Like, is there a case where that can never happen, where that doesn't happen? But if that doesn't happen, then that just means whatever vectors I gave you are not, like, they're not from the same vector space. So you'll always be able to do this. But this is, like, a really special case. Usually what happens is that they give you like, 3 vectors in a 3-dimensional space. But this is like a 3-dimensional subspace of M2R. Right? Because remember, we unraveled some matrices. Right? So this is a 3-dimensional subspace in a 4-dimensional vector space. So there's like some shenanigans going on. But usually, like, there's not. Okay. So, all right, what do? We reduce. What happens? This becomes 1, 0, or 1, 1, 0. So this last row has to be divided by 3 for us to be able to do anything. And then, okay, 0, negative 1, 1. Okay, and now what happens? So I'll need to 0 out. So this last row will stay the same. Up here, I'll do 0, negative 1, and I'll subtract the last row. So this becomes negative 2/3. This becomes negative 1/3, and that's a 1. And then up here, it's still 1, 1, 0. Okay, and now what happens? 0, 0, 1. Negative 1/3, 1/3, 0. So this is all just matrix reducing, row reducing stuff. Multiply the second row by a negative 1. And then the first row, we'll add it to the second row. So over here, we'll add these 2 rows. So now I get 1/3, negative 1/3, and then 1. Okay, and then this is BBC. Okay, and the real question is, right, if I said something like, all right, if I said VB is equal to, right, because remember, let's zoom out a little bit, or not that much. Remember that our inputs are really matrices, right? Right, so we have a base, so these are really matrices. So if I said, here's VB, I have to give it to you in matrix form. 1, negative 1, 3, 4. Right? So now what is VC equal to? Right, so now you say, okay, VC is equal to PBC times VB, and you get this weird thing going on where you have a matrix, and then you want to unravel this, but even if you do unravel it, Oh, okay, no, never mind. I'm doing this wrong. I'm doing this wrong. So this, ignore all this for now. I'm doing this wrong. Okay, if they give you VB, so this is where I messed up. If they give you VB, what does VB have to look like? This is a pretty conceptual question here. But what would VB look like? Yeah. Yeah, it's a 3x1 column vector, right? Because what is VB? If we remember from way up here, remember, here's VB, right? VB are the coefficients in front of my bases. Okay? VC, right? It's 3, 0, 3, 0. These are the coefficients in front of my basis. Right? So if I gave you a matrix for if I gave you something for VB, I would have to give you coefficients in front of my B matrix. Does that make sense? So I can't actually give you a 2x2 matrix because those aren't coefficients. All right, so that's where I messed up because I was like, oh, what if VB is this 2x2 matrix? That can't ever happen. All right, so everything should work out. Yeah.
If they gave you like a matrix, would you have to could you be able to find VB
Yeah, I would say so. They would probably give you something really simple, like if they said let's say they gave you a matrix. Yeah, let's just say VB, or I don't even want to call it VB. Let's say they gave you some matrix A, B, right? And let's say they made it 0, 2, 4, 0, right? Then VB would be 0, 0, 2, right? And then you would plug 0, 0, 2 into here, right? And then VC would also be a column vector matrix, but then you would have to multiply C by the coefficients that you got to get the actual matrix. Yeah.
Could you explain the whole VB and why can't be the 2x2 matrix?
Yeah. So again, so this is kind of bad thing that I did up here for, that I started with this example, but notice that VB and VC, they're the coefficients in front of my bases, right? So yeah, so that's why I was circling like the 3, 0, because it's 3 times this basis plus 0 times that basis, right? So VB is like it's a coefficient vector, right? Down here, right, I can't have VB, like I can't give you a VB equal to like a matrix because that's not a coefficient vector, right? It has to be a coefficient of my bases of B. Okay, so that's why that's what we all went through there. Yeah.
What exactly happens when you get VC in the short example? You still then multiply C by the coefficient?
Yeah. So then you would so now you know like so let's do this example. Let's actually do this example out. So let's say I gave you a matrix A. Uh, 0, 2, 4, 0. All right. Write it in terms of basis C. Okay? So step 1 would be to write in terms of B, basis B. Right? Because for our basis B, we can easily see what that needs to be, right? It's just 2 times the last matrix, right? Because it was 0, 2, 4, 0. Okay? And then what are my basis B? My basis B is up here, right? And we see that it's just 2 times this last matrix. Is everyone okay with that much? Right? We're writing 0, 2, 4, 0 in terms of basis B. And here's my basis for B. Okay? So then, what is that? well, that's equal to 0 times 1, 0, 0, 0 plus 0 times 0, 0, 0, 1 plus 2 times 0, 1, 2, 0 is equal to 0, 2, 4, 0. Okay? So VB would just be these coefficients (0, 0, 2). Okay? And now we take our change of basis matrix which was whatever the heck this was up here. -1, -1/3, 1/3, 0. And we multiply it by 0, 0, 2. Right? Because now this is PBC times VB, and that should get me VC. Yeah.
So if it wasn't as clear, then you would have to go through the whole like row reduction.
Yeah, but it'll be clear. It would be clear. Yeah, yeah, yeah. Yeah.
So if it was just like really obvious how to write A in terms of the basis of C, you would just skip all of this.
Yeah, exactly. But
It's not going to be obvious.
it's not clear, right? So from what we were given, it's not immediately clear, right? From the basis of C given. Yeah. Yeah. Because, well, you kind of just, it's kind of tells. Yeah, because it's just like, it's 2 times that last matrix is equal to the matrix on the left.
And then you can fit zeros for others.
Yeah, exactly.
And then, like, for VB, like, does it have to be, like, a something by one matrix? Why is it?
Yeah, because we're multiplying this change of basis matrix on the left, right? So this is 3 by 3, so this dimension has to be 3 by something, and the only thing that makes that work is 3 by 1. Because your choices were 1 by 3 or 3 by 1.
So, like, all the way at the top, was that graph, like, the 3, 3, what was that?
3, 3?
Yeah.
That was the coefficients in terms of my basis 1, 0, 0, 1, right? Because this is 3 times 1, 0 plus 3 times 0, 1 gets me 3, 3.
So in that case, the VB and VC were like
Yeah. So this thing and this thing are the same thing. They're the same thing. I just wrote them in terms of row vectors with the comma separating them. But those two are like they're the same things. Yeah. Okay. So let's just finish this. So this then is equal to 2, -2, 0. Right? Which means that 0, 2, 4, 0 is equal to, and then where's my basis for C? So these are the B bases. And then my C bases are these guys. Right? And what this is telling me is that, okay, this is 2 times that plus a -2 times the second matrix plus 0 times the third one, where these are my C bases. Is everyone good with what we did there? Okay. I'm going to go overtime because I have more just like the linear transformation stuff I get to. So is that okay with people, or do people need to go? This is all being recorded right now, so. Okay. Any final questions here? Okay. So that's linear transformations. Where do we use change of bases? Well, okay, so linear transformations, right? So there are three types. The first type, type 1, given a map, unspecified basis, or a standard basis. Find the matrix of linear transformation. All right, and this is what we did in recitation. So in recitation, right, we had a map, we had unspecified, or I gave you what the base, or I gave you the standard bases, and then you had to find the matrix of linear transformation. So that's type 1. We're not going to cover that. Type 2 is given a bunch of inputs and corresponding outputs, find the matrix of transformation. So here's an example. Okay, so what's the example? If we take T from P2R to M2R, and we know T of x squared minus x minus 3 is equal to negative 2, 1, negative 4, negative 1. T of 2x plus 5 is equal to 0, 1, 2, negative 2. And T of 6 is equal to 12, 6, 6, 18, right? What is T? So now what we want to do is, okay, so first of all, there's no bases given, right, for this problem. So what should we assume? Yeah, standard basis. So assume standard basis. All right. Now, what do we want to do? All right. Now we need to find the shape of our matrix T. All right. So that means I need to find the dimension of P2R, which is 3. And I need to find the dimension of M2R, which is 4. Right? And so then T is going to be a 4 by 3. Okay? So now what? Now, okay, so what was the next step in the linear transformations, like the regular ones that we saw in recitation? Do you have a question? Yeah. You need to know these for the exam. Yeah, these are just stuff you need to put on cheat sheets. So P2R is the polynomials, right? Dimension 2. The polynomials with power 2 or less. So what's a standard base? So you need to know the standard basis, and you need to know the dimension, right? So that's just I cover those in my recitations, right? We went through standard basis and dimensions. This is stuff that needs to end up on cheat sheets. Yeah. Yeah.
Just real quick, like the standard basis for like P2R would just be like 1x.
Exactly. All right. So yeah. So speaking of standard basis, right? Of the input vector space. In recitation, what we did was we said T of the first standard basis element is equal to what? right? And then we did t of the second standard basis element is equal to what? And then we did t of the third element is equal to what, right? And then we just aggregated everything and put it into a matrix. So now we can't really do that, but what I have is I have t of -3, -1, 1, right? So this is my input, and again, we're thinking 1x squared is equal to, and now I want to unravel that matrix, right? So I just rewrote this guy like that. And then now, same thing, t of 5, 2, 0 is equal to 0, 1, 2, -2. And then lastly, t of 6, 0, 0 is equal to 12, 6, 6, 18. Okay, everyone okay with this much at least? All right, so what do we do next? Well, I'm gonna do something that may not sit well with some people. So stop me if this doesn't seem legal, but it is. So let's say I have t of 6, 0, 0, right? Don't close your parentheses, leave some space. Okay. I know for a fact then that 12, 6, 6, 18 has to go there. All right, so this column ended up here, and then I'm just going to take the second column, and I'm just going to put it here. So then t of 5, 2, 0 is equal to 0, 1, 2, -2. And then finally, t of -3, -1, 1 is equal to -2, 1, -4, -1. Are we okay with this? Are there any objections? So what I did, right, I had my original t, and I unraveled everything and expressed it in terms of column vectors, and now I took these column vectors and I just threw them together into two matrices. Yeah?
Is there any reason you did that order, like you did the 6, 0, 0 first?
Yeah, because we just solve for t, right? And what do we have to do to solve for t? So that falls into what I'm going to do next. What do I have to do to solve for t here? Yeah, so I want to invert this matrix, right? Multiply it on the right, and then multiply that inverse on the right. Okay? And this kind of upper triangular matrix is just easier to invert. So that's why I did it that way.
Can you like choose whichever?
It doesn't matter what order I put those in. I just did it that way because I knew I wanted to invert that way. Yeah.
So is this the same t as the one that's working like?
Yeah.
So how can we put it?
Well, okay, so this is technically A, which is the matrix that represents T. Right? But essentially, we were just writing T because I was solving for my notation. This is, think of T as a matrix at this point. Okay.
So like the t for the transformation is like an actual process of going from one space to the other, but
Right.
like this t is like the actual multiplication of like a matrix.
Yeah, this T is like a matrix right now. Okay. Right? So once we did this, once we unraveled, so when we do this step right here, this is T is a map, and now T is matrix mult, right? So immediately when we unraveled our column vectors like that, T became matrix multiplication. Okay, so now what I have to do is, so T of 6, 5, -3, 0, 2, -1, 0, 0, 1, right? I want to multiply on the left by this inverse. and on the right, sorry, I want to multiply on right by the inverse, which then means I can take this 4 by 3, and then I also multiply the inverse on the right. Yep. So is everyone okay with this? I'm multiplying both sides of the equation by the same thing. Okay? And then now what happens? Well, this here, this is just the identity matrix, right? That multiplied by its inverse of the identity matrix, so they cancel. So I just get T is equal to this guy times this inverse. So let's actually do it out. So this is 12, 0, negative 2, 6, 1, 1, 6, 2, negative 4, 18, negative 2, 1, negative 1. And I'm just going to give you what that inverse matrix is. So this inverse matrix ends up being 1/6, negative 5/12, 1/12, 1/2, 1/2, and 1. Okay, so on the exam, on the exam, you would like actually have to find that inverse matrix, but like it shouldn't be too bad if this problem comes up. Okay. So now we just have to multiply all this out, and so then we see T is equal to 2, negative 5, negative 1, 1, negative 2, 2, 1, negative 3 halves, negative 5 halves, 3, I can't read my own handwriting, 3, negative 17 halves, negative 1 half. And so this is T, this is my matrix. This is my matrix of my transformation. Any questions here? Yeah?
Is that for the second row of the inverse? 0, 1/2, 1/2?
Yeah, so I just didn't write in the zeros.
But no, is it 1/2, 1/2, or 1/2, 3/2?
1/2, 1/2 here, right?
Yeah.
Yeah, I have 1/2, 1/2. Yeah.
So before when we do the input output of like the vector.
Yeah.
And we assume to use the standard basis.
Right.
What if they gave us like a really weird basis? Like how
That doesn't happen with this type of problem. So in order for them to give you weird basis, they need to give you what the map is. Right? There was no map here. Right? I just said we go from here to here, but here's some inputs, here's some outputs. Now give me the matrix of transformation. If they don't give you the map, then you don't have to worry about it.
So for the matrix multiplication, you use this like that matrix times the input we get from the output.
Yeah. Yeah. So you would input a 3 by 1 column vector here, right? It has to be 3 by 1, and that would represent the polynomial, right? Because the polynomial is dimension 3, and then the output would be an unraveled matrix. So then what you have to do is you just have to re-ravel it back to the 2 by 2 matrix form. Okay. Any other questions here? This should be kind of straightforward. Yeah.
Why were you concerned that we were gonna find the first step very weird?
It's just, no, I said this part where we just slapped these columns together into like a bigger matrix.
Yeah.
Right? It's just, sometimes people ask me like why you can do that, which is like a very common like question to ask. But if you like wrote this like abstractly in terms of like V's and W's, like you'll see that you can do that. But I just wanted to like hand wave that part because I don't want to work that out. Okay. Any other questions? You have one? No?
Oh no.
Okay. All right. So one last type of problem. We're gonna tie in everything now. So, all right, we're gonna be done by 6:30. I promise. Okay. Here it is. So we're gonna end on a goodie. This comes from a 2017 midterm exam. And so hold on. I got ahead of myself. But the example does come from 2017 midterm exam. This is the third type of problem. You're given a map, and you're given some whack bases. You want to find TBC. And TBC is just a matrix of transformation. Keeping the bases in mind. So this is where we tie in everything. All right, we tie in the linear transformations, we tie in the change of basis matrices. All right, so part A, so this problem then was the 2017 midterm problem. What you're given is you're given T is from P2R to R2. And you know that T of f of x is equal to f prime at 0, f at 0. Part A is find TBC where the bases B is equal to 1x x squared and C is equal to E1 comma E2. And so the reason why I did this first part is because what the hell is E1, E2? This is just standard bases. So how do we do this first part? Yeah. You don't need to transform the bases. Because what are the bases? Yeah, they're just they're just standard bases, right? Because B is just your standard basis for P2R, and C is just a standard basis for R2. Okay? So this problem, part A, don't overthink it. If B and C are the standard basis, we just plug the input basis into the map and get our output basis. All right? So what we do then is, okay, this is dim 3, this is dim 2. So our matrix is going to be 2 by 3. Yeah. No. R2, XY plane.
Oh, wait, never mind. I was thinking P2.
Yeah, P2 is dimension 3. Yeah. Okay, so now we have this. So what do we do? Well, we do T of 1. What's T of 1? Well, that's equal to f prime at 0, f at 0, which is, all right, what's the derivative of 1? 0, so it's 0 everywhere. It doesn't matter where we evaluate it. All right, and if my function is the constant function 1, right, then what is 1 evaluated at the point 0? It's just 1, right? So it's just y equals 1 laying down, and then if you let x equal 0, well, you still go to 1. T of x is equal to, all right, what's the derivative of x? 1. All right, and then we have x, but now we have to evaluate x at 0, so that's 1, 0. T of x squared is equal to, what's the derivative of x squared? 2x, and then we got x squared, but now we have to evaluate these at 0. Okay? Everyone happy with this so far? Good? So now what do I do? This is t of 1, which is 0, 1. This is t of x, which is 1, 0. And then here I have t of x squared, which is 0, 0. So this is my matrix for part A.
What is like t of x equals 1x?
It's just because you have f prime of 0 and f of 0, right? So t of x just means I plug in x into my map, which is f of 0, f prime of 0, and f at 0. Okay? So you plug in x into f prime at 0. What's the derivative of x? 1. And then you evaluate it at 0. Right? So the derivative of x is 1, and then you evaluate it at 0, that's still 1. Right? And then the bottom one is f at 0. So if you plug in x into the map, right, this is what f is. Because it's t of f, but then f is equal to x. So now that's x, and then you evaluate x at 0. So you get 0. Yeah.
Why did you choose to have like 1x and x squared again?
1x, x squared. It's because that's my basis. Right? So remember in recitation, this is the type 1 type of problem where you're given the standard bases in both input and output spaces. So all you have to do is plug in the input basis into your map and see where they go. Yeah.
What if you weren't given a standard basis, but it would have been different?
That's the next part. Yeah. That's the next part of this problem. Okay. Any questions with this first part? This is literally what I did in recitation 8. Recitation 8. Okay. Part B is the following. Find TBC where B is equal to 1 plus x, 1 plus x squared, C is equal to 1, 2, 2, 3. Yeah.
Like the 0, 1, 1, 0, 0, 0, put it into that 2 by 3.
Yeah.
How is that different from the problem that you did before where you took t times like 6, 0, 0, 5, 0?
In that problem, you were given this. Right? But these inputs here, like this x squared, this x, that 1, they're not your basis elements. But 1x and x squared are your basis elements. Right? So in the previous problem, we need to express that transformation in terms of our standard bases. Right? So to find any matrix of transformation, we have to see where the bases go. But in that problem, I did not know where the bases went. I knew where a bunch of random crap went. Does that make sense? Okay. But here, since I do know I have a standard basis, I can just plug in my standard bases. All right, anyways. So now, here's this problem. Right? And you'll notice your basis is 1 plus x squared, and x squared. So that's just not your standard bases, right? And then C, instead of being 1, 0, 0, 1, or E1, E2, which is your standard basis, C is this random stuff right here, right? It's just a random basis. So now, what do we do? Step 1, find T, B, I'm calling E. Where E is the standard basis of output. So this step 1 is literally the same thing as we did above. All right, you just plug in your basis into the map, see where it goes, and just make the matrix. All right, here you don't have to like worry about doing any like basis changing. So again, we're going to have a 2 by 3 matrix, right? And I'm going to do t of 1 plus x, t of 1 plus x squared, and t of x squared, right? So above, right, I just plugged in these bases into my map that were given in B, right? Down here, we're going to do the exact same thing. All right, it's just that these bases are a little different. Yeah?
I didn't know that whatever comes out of that map is going to be the standard.
Because it has to be, right? Because you're plugging stuff in, you're taking derivatives, and then you're evaluating it. Well, that number has to have some kind of meaning behind it, and like just the default meaning that comes out of it is in the standard basis. All right? So you kind of see where this is going? Is that we output it in the standard basis, and then we do a change of basis into whatever the crap that is. So yeah, so whatever comes out of these evaluations is going to be in the standard basis in step 1. So this was, right, so remember our map was f prime at 0, f at 0. So what's the derivative of 1 plus x? 1. And then here it's just 1 plus x. But now I have to evaluate it at 0. So that's 1, and the bottom part becomes 1 plus 0, so that's just 1. Okay, step 2, same thing. All right, what's the derivative of 1 plus x squared? Yeah, 2x. And then down here, it's just that map again, 1 plus x squared, or that function. All right, and now I have to evaluate it at 0. 0, 1. Okay, now x squared. Well, x squared is the same thing as the x squared above. So this was 2x, this is x squared, and you get 0, 0. Okay, so this first map right here, this is TBE to the standard bases, and it's going to be t of 1 plus x, which is 1, 1, t of 1 plus x squared, which is 0, 1, t of x squared, which is 0, 0. Okay, so what do you think step 2 is? Yeah. From? What is that? So if I plug in something in here, what basis are my outputs in? E. E, right? Because this is TBE.
You're looking for the one.
But I'm looking for the one in C. So what do I need to have my basis be changed to? E to C, exactly. So step 2. Is to find P from E to C, right? Or PEC, right? They're the same thing. But I want you to be able to stare at this long enough to get to this, because it makes the calculating the change of basis stuff look really easy. You know what goes on what side. Okay. So now, this is what I need. I need C on this side, I need E on this side, right? First of all, okay, so what is C? Yeah, 1, 2, 2, 3. All right, so what is E? Yeah, it's 1, 0, 0, 1. Okay, so change of basis comes back. We reduce this thing. 1, 2, 0, negative 1. 1, 0, negative 2, 1. And then this becomes 1, 0, negative 1. Oh, negative 3. 2, 0, negative 1, negative 2, 1. And then one more reduction. 1, 0, 0, 1. Negative 3, 2, 2, negative 1. What is this? Okay, so this is the identity matrix, and this is P, E, C. Yeah.
Did you go over how you got C and E?
C is given. Right? So I just put them in the columns. All right. E is the standard basis in your output space. All right, so what's my output space? Which one's my output space? T from P2 to R2. Which one's going to be the output space? R2 is my output space, right? So E is the standard basis for my output space, which is 1, 0, and 0, 1. So then I just put 1, 0, and 0, 1 into E. All right. Okay. Everyone okay here? We found change of basis matrix again. So it came back. What's step 3? We want to find TBC, right? Yes, we multiply them, but, right, multiply, but in what order, right? So so what do we have? We have TBE and we have PEC, right? So if you do this way, what's really going on is you're saying this is TBE and this is PEC. Well, you're saying we're in basis E to start out with. We change it to basis C, and then what? All right, so that doesn't work. This isn't the way to do it. All right, the way to do it is to say PEC times TBE, because now you got PEC TBE. Oh wait, I just wrote the same thing. You got PEC TBE, because what's going on? You're taking an input from basis B, right? You take an input from basis B. And what is basis B? Remember, basis B way up here, right? So here's our map. You're taking a basis B, which is a polynomial, all right? You take that in, you output it to the standard basis. So this is basis B of P2. This is standard basis of R2, right? Since now you took the polynomial in, T spits you out something in R2, and now this change of basis takes in whatever you spit out and then gives you a vector in R2 in terms of basis C. And so this is going to be TBC, because we took in an input from basis B and we outputted something in terms of basis C, and that's exactly what I had to do with TBC. Okay? So then all we have to do is write these down and multiply them. -3, 2, 2, -1 times 1, 1, 0, 1, 0, 0 equals -1, 2, 0, 1, -1, 0. So this is TBC. 6:29. I said I'll be done by 6:30. All right. Any questions? Yeah. Sorry, the what? So P is always change of basis. It's always labeled as P. Because if you remember way up here, like way up in the change of basis section, right? This was the change of basis matrix. It was called P, right? And then T, so T just tells me it's a map that can be to different vector spaces, right? But remember, change of basis has to be the same vector space. So P has to be square, right? And it is. P is square. T doesn't have to be square inside. So that's kind of the case. All right, so this is it. I'll upload this, and then we're going to be right back here tomorrow at 7, and I'll be doing a bunch of problems. So I won't be like explaining this stuff. We'll just be going from point A to point B on problems.
So just like a really quick follow-up, I think to what she was asking.
Yep.
So both of these are like the anti or both matrices that you multiply like something might go to another thing.
Right.
But for P, it's specifically you have to be the same vector space.
Yes.
So are you going from like one, like?
P is change of basis.
Are you going from, yeah, so when you say like you're in the same vector space, are you going from like one subspace to another subspace, or
You're literally you're in R2, you have your axes, and you rotate them. Or you like squeeze them or something.
Okay.
And then you have new coefficients to describe whatever point you had, and that's what we're doing with PBC.
P, okay.
Yeah.
TBC, you're
Right.
TBE, wait, TBC. Well, I guess, okay, yeah. So like for that, what are, like, that's a map where you literally go from one space
to another space, right.
Well, like both of them are going to be matrices that you multiply the vector by.
Right, exactly.
And I'll give you like your new thing.
Exactly.
I thought I knew what a transformation was, but I think I don't.
So transformation is just you take an input from a vector space,
Yeah.
and you spit out an input in another vector. You spit out some output in a different vector space.
Is it always in a different vector space?
No. No, it doesn't have to be.
Okay.
So if you watch recitation 8,
Yeah.
I do an example where the transformation is in the same vector space. It's like the most basic type kind.
Okay.
Yeah. Who was? I think you were in line first.
Oh no, they can go.
Okay.
Hi. I was just wondering, this is like, C is vector,
Yeah, R2. Yeah.
So what is that? Why is that?
Why
so
is
these
that?
are these are bases.
Right. So T, right?
Yeah.
So what does T do? So T is like this first thing I wrote up here. Where's my pen? Oh, it's over here. Okay. So right, T is my map.
Yeah.
Right? It takes in an input from P2 and it spits out an output in R2. Right? So T takes in an input in R2, P2,
and
spits out an output in R2, right? But then P takes that, changes the basis, and then changes it to this.
Okay.
Right?
Thank you
So
much.
that's what's going on. Yeah.
I was just confused about like, I assume that this is kind of similar. And
Yeah,
that's
it's
like
exactly what
calculation,
we were doing.
But I can't really like figure out exactly like how it's happening. It's like here, like I get that you just
Here, don't follow what the book is.
Okay.
Go home, follow these 3 steps, and see
Okay.
if you end up with the same matrix. If you do, you're good.
Okay.
Right? Because the way they're doing it is they're saying, so this is essentially the first step. You send T
Right.
of t of your basis element into the normal basis,
Right.
and then you need to express it in terms of c.
Okay.
So that's what they're doing. They're
Okay.
taking the first element in this basis,
Right.
right? And then they're expressing it in t. They're putting it in the input. They're spitting out an output,
Right.
and they're taking that output and expressing it in terms of basis c, which
Okay.
is right here,
Okay.
right? Or up here, which is the first.
Okay.
Right.
Okay.
So the idea is when you have the standard bases,
Mhm.
right, which is this guy and this guy,
Yeah.
right, you don't have to do like that whole change of basis multiplication
Right.
stuff, because once you spit out your output, you're done.
Okay.
Yeah.
Thank you.
So I would do this B part
Yeah.
and see if you can end up here.
Okay.
Yeah.
Thank you.
Yes.
You can go ahead.
Are you sure? Okay.
Yeah.
You were in
No, here, I'll answer your question. It's fine.
Well, no, like I have like multiple questions and they're not really like structured, so I'm letting everyone.
Sure.
So, do you know that question that you transformed the f on one of the homework? It was like there's
Yeah.
Would there be something similar to that on the
Sure, there could be, but
like it's
yeah,
a possibility.
it's possible. Yeah, everything on
So,
the
like,
homework.
That, yeah.
Yeah. So are you asking like how do you see that in terms of linear transformation?
No, I think, because for the transformation there was one where it's like 1,
Mm-hmm.
and it's like some cosine sine thing going on. Is that what?
Yeah. So there's this thing called a rotation matrix
Yeah.
where it's just like cosine theta.
Yeah,
I don't
cosine.
ever.
Is that?
This is rotating it in some
That's
way.
how I did it in the homework.
Right. No, but so this is how you want to do it. What you want to do is you want to say, okay, so everything started out with, right? Right? Like this. We take a basis for f, which is 1, 0, 0, 1, right? And then we see where it went. So if it went here,
So the example is like this, and it's like stretch horizontal.
yeah. So if it's like this, right? Right, something like this, it was like that, right? So what happened was 1, 0, t of 1, 0, right, which is this guy, still ended up being 1, 0.
Yeah.
Okay? But t of 0, 1 ended up being 1, 1. Right? So now you have the second type of linear transformation problem. Right?
It's doing like cosine.
Right, exactly. But if you invert this, it's just identity matrix, so it's whatever. T is just equal to that thing. Yeah. So that's how you wanted to approach those problems. Which was kind of weird that he had it that early on the homework.
I know, I had no idea how to do that.
Yeah.
I actually have a question about that, too, specifically.
Okay.
So, I was like cheating, I think. Like, I was doing some fake stuff. It wasn't real math at all. Like, I was just looking at it and like guessing. And
Yeah, that's kind of what it is.
but like, it was so, like, I had no idea. I was just like, well, you know, this point ends up over
Yeah.
here.
No, that's so this was like, there was like ax plus v, right? That was like the problem. It was like t is equal to ax plus v.
Yes.
Yeah, so you had to see where the origin ended up to find out what v is. So that was
I
legit,
did
but
that by accident.
yeah, but the a part is this is how you found a. So this should be
Okay.
a.
Oh, wait. Okay. Yes. So that's why I was confused that it was in a different vector space, because like if you linearly transform something, isn't it just still?
No, you can have linear transformations between different vector spaces.
This one just happened to be in the same
Yeah, that's
vector
what just
space?
happened to be in the same vector space. Whenever you have a geometric example, it's really hard to show different vector spaces.
Yeah.
But like in theory, yeah, you can go from one vector space to just a completely different vector space.
Okay. And like, I don't know. I just don't think I understand. I'm like, see, because like at first I thought I only understood linear transformations and not bases, and now I only think I understand bases and not at all.
I mean, you have.
It's like I get
a lot
one
of
and then I completely lose concept of the other one. Like first, I was like, oh, you take something, you multiply by a matrix, it spits out a new, like easy, that's fine. But now, that seems like that's not actually what's happening, but it is.
It is. It is.
Why is it so hard?
I think you're just getting caught up on the fact that you can go from one different vector space to another one, right? So if you just drop that, so this is how you.
Like, okay, are these grids still the same? Like the
Yeah,
basis
yeah,
hasn't
yeah,
changed.
yeah. The grids. So fundamentally, like the way we can say this is 1-1 is because we had a standard basis.
Right?
Right.
Yeah. Okay.
So that's we briefly mentioned that in the review session here, where people ask about it. Yeah. So in order for this change of basis to have any meaning, like you
Wait,
had
this
it.
isn't a change of basis then.
Oh, sure, but for this map to have had any meaning, like even in a change of basis, you needed to have had like a defined standard basis.
Yeah.
Yeah. Because everything like
Yeah,
is.
obviously. I mean, if you have to have axes. If you have axes, you have basis.
Exactly.
Okay.
All right.
Like, first off, when are your office hours this week? Do you have any?
They're on my website. I'm gonna
Okay,
change.
I'll check them.
I'm gonna change the Wednesday one, but I'll send out an email because I have an exam at 1 p.m. on Wednesday, so I'm gonna move my office hours to after that. Yeah.
So to clarify, a change of basis will always happen under the same
Vector space, right? Because there's a change of basis.
Right, just the way we look at everything being made in that space.
Right.
A linear transformation, though, is a change of vectors. Is a change from one space to another.
Could be.
It could be. It doesn't have to.
Yeah, it doesn't have to be, but it could be.
Okay, so okay, and then that means in that case there's always going to be a matrix that can multiply by that vector, which is the input in the transformation.
Yeah.
And that can always give us the same output.
Right.
Okay. Okay, that makes sense. And then I want, like, what is, I don't know what he means by this. Okay, let's see. He tells us the breakdown. Column space and nullity. Isn't
that's
that
column space? Null space.
Isn't it the same thing?
Yeah.
Column space and nullity. Column space and nullity.
It's NA is null space, but
right.
it's like
so
it's
nullity,
the same.
It could be referring to like
null space problems.
Nullity rank theorem.
Yeah,
possibly.
exactly.
But okay, so they're not the same type of problem necessarily.
They're not. They test over that concept. Those are the concepts on the exam.
Okay.
Yeah.
So when he has it twice, which just means it could be two problems like that.
No, it literally means problem 4 could have problem 4 could have column space and it could have eigenvalues, right? Or
because he has 3 and 4 have the exact same stuff.
Yeah, that just tells you what that problem can be.
So they could both be the same types of problems.
Right.
Okay.
Right. He's just narrowing down each problem to what you could be tested on that problem.
To show how much a certain topic is.
Right. Exactly. So you'll notice that eigenvalues have a kind of large weight for being this late.
Yeah.
But I mean, eigenvalues are more like a computational thing.
Yeah, I like them a lot. Other stuff is.
I mean, yeah.
crazy.
I have a question about the eigenspace. What is it?
Eigenspace is just.
Is it just the space defined by the eigenvectors?
It's the span of the vectors.
Yeah, span of the eigenvectors.
Yeah.
The eigenspace is just.
Span of the eigenvectors.
Exactly.
That is what I thought. Oh, how